Hello, deep divers! Welcome back to the channel. Today, we read tackling one of the most famous ideas in all of science, Albert Einstein's theory of relativity. It reshaped our understanding of the universe, predicted black holes, and even affects your GPS. But what does it actually mean? Let's dive in. For over 200 years, Isaac Newton's laws were the rulebook. They worked perfectly for planets and apples. But by the late 1800s, physicists hit a snag with light. They thought light waves needed a medium to travel through, called the luminiferous ether. But a famous experiment in 1887 by Michelson and Morley found something astonishing. Light as speed never changed, whether you were moving toward it or away. Physics was stuck. Then, a 26-year-old patent clerk named Albert Einstein changed everything. Einstein's genius was in his thought experiments. As a teenager, he imagined chasing a beam of light. If he caught up, he reasoned, the light wave should appear frozen. But the laws of physics said that was impossible. This paradox bugged him for a decade. His solution? To deceptively simple postulates for his 1905 theory of special relativity. First, the laws of physics are the same for everyone, no matter your constant speed. This wasn't entirely new. Second, and this is the revolutionary one, the speed of light is always the same. It doesn't matter if you're running toward a light source or away from it. You'll always measure it at 186,282 miles per second. Accepting these two ideas leads to some mind-bending consequences. Einstein illustrated this with a train. If two bolts of lightning hit a moving train simultaneously for someone standing still, a person on the train would see them hit at different times. This is the relativity of simultaneity. Events that are simultaneous for one observer may not be for another. If time isn't absolute, what else changes? Three incredible effects emerge. 1. Time dilation. Moving clocks run slow. An astronaut traveling at near light speed would age slower than people on Earth. 2. Length contraction. Objects in motion shorten in the direction they're traveling. 3. Mass-energy equivalence. This is the big one. Mass and energy are two forms of the same thing. And Einstein gave us the equation E equals mc. That c squared is the speed of light squared a huge number. It means a tiny amount of mass holds a colossal amount of energy, explaining the power of stars and nuclear physics. This isn't just abstract theory. Special relativity is essential for your GPS to work. Satellites are moving at 14,000 kilometers per hour relative to Earth. Their onboard atomic clocks experience time dilation, running about 7 microseconds slower per day. Without correcting for relativity, your navigation would be off by miles within minutes. A decade later, Einstein expanded his ideas to include gravity with his theory of general relativity 1915. His key insight: gravity isn't a force pulling you down. It's the curvature of spacetime itself. Imagine spacetime as a stretched sheet. A heavy planet sits in the middle, creating a dip. A rolling marble, another object follows the curve of that dip. That's orbital motion. It's why light bends around massive stars. General relativity predicts the most extreme objects in the cosmos, black holes and gravitational waves, both of which we've now observed. It's our best description of the universe on a large scale, though unifying it with quantum mechanics remains physics' greatest challenge. So, from a teenager daydreaming about light beams to a theory that explains your road trip and the fate of stars, Einstein's relativity shows us a universe far stranger and more wonderful than Newton ever imagined. It's a testament to the power of human curiosity and imagination. If you enjoyed this deep dive, smash that like button, subscribe, and hit the bell so you don't miss our next exploration of reality. What scientific concept should we unravel next? Let me know in the comments below. Until next time, keep diving deep.